The Pacific Ocean covers nearly half the planet. Beneath its surface lies a secret older than civilization itself. A hidden network of fire and stone, stretching across the seafloor like the veins of a sleeping giant. For millions of years, the Earth's crust has torn itself apart here, piece by piece, building mountains no human eye has ever seen. And sometimes, the giant wakes up. November 20th, 2013, 600 kilometers south of Tokyo, a Japanese patrol helicopter is making a routine flight over the remote Ogasawara Islands. The pilot sees something impossible. The ocean is on fire. From the depths, nearly 1,000 meters below, magma has broken through. It rises with the force of a freight train. Superheated rock meets freezing seawater. The result is catastrophic. This is not a disaster. This is creation. Within hours, a new island begins to rise. The Japanese name it Nishinoshima Western Island, though it is unlike anything seen in modern times. By the end of the first week, it is already 200 meters wide. For scientists, this is a once-in-a-generation event. A volcanic island born before cameras. Born in real time. Dr. Setsuya Nakata, a volcanologist from the University of Tokyo, is among the first to reach the site. He has studied volcanoes for 30 years, but he has never seen anything like this. This is not just an eruption. This is the Earth building itself. Right in front of us, Nishinoshima sits atop one of the most violent seams on Earth, the Pacific Ring of Fire. Here, the Pacific Plate collides with the Philippine Sea Plate, grinding downward into the mantle at nearly 10 centimeters per year. As the oceanic crust descends, it melts. The molten rock, lighter than the surrounding stone, rises. It searches for weakness, for cracks, for escape. And on November 20th, 2013, it found one. Nishinoshima is not alone. It is one island in a chain of underwater volcanoes stretching for hundreds of kilometers. Most will never break the surface, but Nishinoshima did. In the days that follow, the eruption does not stop. It intensifies. Lava fountains shoot 100 meters into the air. Ash clouds darken the sky. The island grows. By December, Nishinoshima has merged with an older, smaller island nearby. By March 2014, it is over 1 kilometer wide. By the end of the year, it has grown to twice the size of the original island. This is not a slow birth. This is explosive growth. Each day, Nishinoshima releases thousands of tons of lava. The magma is basaltic, dark, fluid, and relentless. It pours from vents in thick rivers, glowing orange in the night. For 18 months, the eruption continues without pause. A permanent column of ash rises into the atmosphere. Ships are warned to stay clear. Aircraft are rerouted. This is a no-man's land, a place where the Earth is still writing its own story. For geologists, Nishinoshima is more than a curiosity. It is a laboratory, a window into the distant past. This is what Earth looked like in its infancy. A planet of fire and stone constantly remaking itself. Every rock, every ash particle, carries information. About the mantle, about the forces deep below, about how worlds are born. Dr. Nakata returns to the island multiple times. Each visit reveals something new. We are watching a planet breathe. By 2015, Nishinoshima is no longer a curiosity. It is a landmark. A new piece of Japan. A reminder that the Earth is not finished. But 6,000 kilometers away, across the Pacific, another fire is stirring. And this time it will not go unnoticed. The Alaskan Sentinels. Alaska is a land built by fire. 52 active volcanoes line its southern coast like teeth along a predator's jaw. They are part of the Pacific Ring of Fire, the same tectonic boundary that gave birth to Nishinoshima. But here, the violence is older, deeper, more patient. The Alaska Peninsula stretches southwest from the mainland like a crooked finger pointing toward Russia. Along its spine runs the Aleutian Range, a chain of snow-covered peaks that have erupted for millions of years. Some are famous: Mount Redoubt, Mount Spur, Augustine. Others are known only to scientists and the indigenous communities who have lived in their shadows for thousands of years. The Aleut people call them the Smoking Mountains. They have watched them for generations. They know the signs. When the birds leave, when the rivers run warm, when the air smells of sulfur. These are the languages of the Earth, spoken in warnings no instrument can measure as precisely as human memory. For the volcanologists of the Alaska Volcano Observatory, these mountains are not just geological features. They are responsibilities. The AVO operates out of Anchorage, Fairbanks, and the USGS headquarters in California. Their mission is singular: monitor every volcano in Alaska capable of threatening human life or aviation. That means watching more than 50 peaks simultaneously, using seismometers, satellite imagery, gas sensors, and webcams. It is a monumental task. Alaska is larger than Texas, California, and Montana combined. Much of it is wilderness. Roads are scarce, access is difficult. In winter, it is nearly impossible. Before we continue this story, subscribe to the channel. Your support helps us tell the true stories of Earth's most powerful volcanoes. But the volcanoes do not wait for good weather. In early 2013, while Nishinoshima was beginning its dramatic birth in the western Pacific, several Alaskan volcanoes began showing troubling signs of unrest. Pavlof, one of the most active volcanoes in North America, started rumbling in May. Located near the tip of the Alaska Peninsula, Pavlof is a near-perfect stratovolcano, its symmetrical cone rising 2,700 meters above the Bering Sea. It erupts frequently, sometimes multiple times per decade. But this time felt different. Seismic activity increased. Small earthquakes clustered beneath the summit. Then, the tremors became continuous, a phenomenon volcanologists call volcanic tremor. It sounds like a low hum, a vibration deep in the Earth's throat. It means magma is moving. Pavlof was waking up. On May 13, 2013, Pavlof erupted. Lava fountains burst from the summit crater, arcing into the sky and tumbling down the flanks in glowing rivers. Ash plumes rose 8 kilometers into the atmosphere, drifting east across the Gulf of Alaska. The Alaska Volcano Observatory raised the aviation color code to red, the highest alert level. Aircraft were diverted. Flights were canceled. The eruption lasted for weeks, pulsing with unpredictable intensity. But Pavlof was not alone. Just 200 kilometers to the northeast, another volcano stirred. Veniaminof, one of Alaska's largest and most dangerous volcanoes, began showing signs of renewed activity. Veniaminof is a giant. Its caldera is 10 kilometers wide, filled with ice and punctuated by a central cone that smolders almost constantly. It sits near the communities of Purryville and Chignik, villages with populations measured in dozens, not thousands. But they are directly in the path of any major eruption. Veniaminof had been erupting intermittently since 2013, but in June the activity escalated. Lava flows emerged from the central cone, melting ice and sending meltwater flooding down the flanks. Ash emissions increased. The seismic network recorded hundreds of small earthquakes daily. The AVO issued warnings. Residents were advised to prepare evacuation plans. Some left voluntarily. Others stayed, watching the mountain with the calm fatalism of people who have lived with volcanoes their entire lives. Then, in August, Cleveland Volcano joined the chorus. Cleveland is a remote island volcano in the Aleutian chain, rising abruptly from the Bering Sea. It has no permanent population, but it lies directly beneath major air routes connecting North America and Asia. Tens of thousands of passengers fly over it every week. Cleveland is notorious for producing explosive eruptions with little warning. It has destroyed aircraft in the past. In 1944, a military plane flew into an ash cloud from Cleveland and crashed, killing all aboard. On August 8th, Cleveland erupted without warning. A satellite detected a thermal anomaly at the summit. Hours later, ash was streaming into the sky. The eruption was brief but violent, sending a plume 12 kilometers high. Airlines were forced to reroute flights. The economic cost was immediate. Fuel consumption increased. Schedules were disrupted. Passengers were stranded. All because a mountain on an uninhabited island decided to exhale. For the scientists at the Alaska Volcano Observatory, this was not coincidence. 3 major volcanoes erupting within months of each other was unusual but not unprecedented. Alaska's volcanoes are part of the same subduction system. The Pacific Plate is diving beneath the North American Plate at a rate of 6 centimeters per year. As it descends, it melts, feeding magma chambers beneath dozens of volcanoes. When pressure builds in one part of the system, it can trigger activity elsewhere. The Earth's crust is not a collection of isolated mountains. It is a connected system, a web of fire stretching from Alaska to Japan to Chile. But there was something else. Something the scientists were beginning to notice. Nishinoshima was still erupting in the western Pacific. Pavlof, Erupts, and Cleveland were erupting in Alaska. And across the Pacific Rim, other volcanoes were stirring, Sinabung in Indonesia, Colima in Mexico, Villarca in Chile. The Ring of Fire was not just active. It was synchronized. Was this normal variation? Or was the planet entering a more active phase? The data was inconclusive. Volcanic eruptions are common. At any given moment, 20 or more volcanoes are erupting somewhere on Earth. But the clustering, the timing, the intensity, it felt significant. The Alaska Volcano Observatory increased monitoring efforts. More seismometers were deployed. Satellite surveillance was intensified. Webcams were installed on remote peaks. The scientists worked around the clock, analyzing data, issuing forecasts, trying to stay ahead of the mountains. Because in Alaska, the stakes are uniquely high. The state sits beneath some of the busiest airspace in the world. Ash clouds from Alaskan volcanoes can shut down international aviation for days. A single eruption can cost airlines hundreds of millions of dollars. And the people who live near these volcanoes, they do not have the luxury of leaving. For the residents of Cold Bay, King Cove, Prairieville, and dozens of other small communities, the volcanoes are neighbors. Dangerous neighbors, unpredictable neighbors, but neighbors nonetheless. They have learned to live with the threat, to read the signs, to prepare for the inevitable. Because in Alaska, the question is never if a volcano will erupt. The question is when, and which one, and whether anyone will be ready. The Pacific Ring of Fire is not a metaphor. It is a geological fact. A 40,000-kilometer arc of volcanoes and seismic faults encircling the Pacific Ocean like a noose. It contains 75% of the world's active volcanoes. 90% of the world's earthquakes occur here. It is the most violent tectonic boundary on Earth. The ring stretches from New Zealand through Indonesia, the Philippines, Japan, the Kamchatka Peninsula, Alaska, and down the coasts of North and South America to Chile. It follows the edges of the Pacific Plate, where oceanic crust collides with continental margins and subducts into the mantle. The process is slow, inexorable, and utterly destructive. For most of human history, the volcanoes along this ring erupted in isolation. A mountain in Japan would explode. Years later, one in Chile would follow. The events seemed unrelated, random, but modern monitoring has revealed a different story. The volcanoes are not independent actors. They are nodes in a connected system. When stress builds in one part of the ring, it can propagate along the entire boundary. The Earth's crust does not break in neat, predictable ways. It fractures like ice under pressure, cracking in patterns that cascade across continents. By late 2013, the Ring of Fire was entering one of its most active periods in decades. Nishinoshima was still growing in the western Pacific. Pavlof, Erupts, and Cleveland were erupting in Alaska, but the unrest was spreading. On November 3rd, Mount Sinabung in Indonesia erupted after 400 years of dormancy. The explosion was sudden and catastrophic. Pyroclastic flows swept down the flanks, incinerating everything in their path. Entire villages were buried under meters of ash. 16,000 people were evacuated. Dozens died in subsequent eruptions over the following months. Sinabung sits on the island of Sumatra, part of the Sunda Arc, a subduction zone where the Indo-Australian plate dives beneath the Eurasian plate. It is one of the most seismically active regions on Earth. The 2004 Indian Ocean earthquake and tsunami originated here, killing over 200,000 people. The tectonic forces that caused that disaster are the same forces feeding Sinabung and dozens of other Indonesian volcanoes. Halfway around the world, Colima in Mexico began showing signs of renewed activity. Colima is one of North America's most dangerous volcanoes. It has erupted more than 40 times since the 16th century. It sits near the city of Colima, population 300,000. In January 2014, a series of explosive eruptions sent ash plumes 4 kilometers into the sky. The government evacuated nearby villages. Scientists warned that a larger eruption could follow. Colima is a stratovolcano, steep-sided and unstable. Its eruptions can be sudden and violent. Pyroclastic flows can travel at hundreds of kilometers per hour. There is no outrunning them. Then, in early 2015, Villarca in Chile erupted. Villarca is one of South America's most active volcanoes. It sits near the tourist town of Pucón, a popular ski destination. On March 3rd, a violent explosion ejected lava and ash high into the night sky. The eruption was brief but intense. Lava fountains illuminated the darkness. Ash rained down on surrounding communities. 3,000 people were evacuated. The eruption was captured on video by tourists and locals, the footage spreading across the internet within hours. The images were spectacular and terrifying. A curtain of fire rising from the earth. Volcanoes separated by thousands of kilometers were erupting within months of each other. Some dismissed it as coincidence. Volcanic eruptions are common, they argued. With hundreds of active volcanoes worldwide, clusters of activity are statistically inevitable, but others were not so sure. The timing was striking, the intensity was unusual, and the volcanoes involved were not minor peaks. These were major stratovolcanoes, capable of catastrophic eruptions. Dr. Eric Clementi, a volcanologist at Denison University, studied the data carefully. He noted that while the Ring of Fire is always active, certain periods show elevated activity across multiple regions simultaneously. These periods often coincide with increased seismic stress along major plate boundaries. When a large earthquake occurs, it can trigger volcanic eruptions hundreds of kilometers away by changing the pressure within magma chambers. The 2011 Tohoku earthquake in Japan, for example, was followed by increased volcanic activity across the region. But there was no single mega-earthquake in 2013 or 2014 that could explain the widespread unrest. Instead, it appeared that the entire Ring of Fire was responding to a gradual buildup of tectonic stress. The Pacific Plate, the largest tectonic plate on Earth, was shifting. Subduction zones around its perimeter were adjusting. And the volcanoes, sensitive to even tiny changes in pressure, were reacting. The Alaska Volcano Observatory, the Japan Meteorological Agency, the Indonesian Center for Volcanology and Geological Hazard Mitigation, and dozens of other monitoring agencies were sharing data in real time. They were watching the planet respond to forces beyond human control, and they were trying to predict what would happen next. Because the eruptions of 2013 and 2014 were not isolated events, they were warnings. The Earth was restless, and the Ring of Fire was far from finished. In Alaska, the volcanoes continued to rumble. Seismic activity beneath Pavlof remained elevated. Veniaminoff was still producing occasional ash emissions. Cleveland remained unpredictable, capable of explosive eruptions at any moment. And further west, along the Aleutian chain, other volcanoes were beginning to stir. Shishalden, one of the most symmetrical volcanoes in the world, showed increased thermal activity. Satellites detected heat at the summit, indicating fresh magma near the surface. Akutan, a volcano near a fishing community of the same name, recorded swarms of small earthquakes. Makashian, overlooking the city of Unalaska and its vital port, exhibited elevated sulfur dioxide emissions. Each sign taken alone might mean nothing, but together they painted a picture of a volcanic arc under stress. The people living in these regions understood the danger. In Alaska, volcanic eruptions are not abstract threats, they are part of life. Residents keep emergency supplies. Schools conduct evacuation drills. Airlines monitor volcanic activity as closely as weather. Because when a volcano erupts in Alaska, the consequences are immediate and far-reaching. Ash clouds can ground flights across the Pacific. Lahars can destroy bridges and roads. Tsunamis generated by submarine eruptions or flank collapses can devastate coastal communities within minutes. And yet, despite the danger, people stay. They fish the rich waters. They hunt the abundant wildlife. They live in some of the most beautiful and unforgiving landscapes on Earth. Because Alaska, like the entire Ring of Fire, is a place where creation and destruction exist side by side, where the planet's power is on full display, where the ground beneath your feet is never truly still. By mid-2015, the question was no longer whether the Ring of Fire was active. It was how long the activity would continue, and which volcano would erupt next. By the spring of 2015, Nishinoshima was no longer a newborn island. It was a geological phenomenon. What began as a small eruption on the seafloor had become one of the most sustained volcanic events of the 21st century. The island had been erupting continuously for nearly 18 months. It showed no signs of stopping. Satellite imagery revealed the extraordinary transformation. The island had grown from a few hundred meters across to more than 2 square kilometers. Its coastline expanded daily. Lava flows poured into the ocean in multiple locations, hissing and steaming as molten rock met cold seawater. The island's central cone rose steadily, building itself layer by layer with each new eruption. By June 2015, the summit reached over 140 meters above sea level. It was no longer just an island. It was a mountain being born. The eruption style was primarily effusive, meaning lava flowed relatively gently from vents rather than exploding violently into the sky. This allowed the island to grow steadily without destroying itself. The lava was basaltic, dark and fluid, spreading across the surface in broad sheets before cooling into black volcanic rock. Occasionally, more explosive activity would punctuate the steady flow. Strombolian eruptions sent glowing lava bombs arcing through the air. Ash plumes rose hundreds of meters, drifting eastward on prevailing winds. For the Japanese Coast Guard, monitoring Nishinoshima became a constant operation. Ships maintained a safe distance, observing from beyond the exclusion zone. Aircraft flew regular reconnaissance missions, capturing high-resolution images and thermal data. The island was too dangerous for direct human access. The ground was unstable. Volcanic gases saturated the air. Explosions could occur without warning. But from above and afar, scientists could watch the island's evolution in unprecedented detail. Dr. Setsuya Nakata and his team analyzed the data obsessively. They measured the volume of lava being produced. They tracked changes in gas emissions. They monitored seismic activity beneath the island. Every piece of information helped them understand what was happening deep below. The magma feeding Nishinoshima was rising from a chamber several kilometers beneath the seafloor. It was being supplied continuously, suggesting a large and active source. This was not a brief pulse of magma. It was a sustained eruption fed by a robust plumbing system connecting the surface to the mantle below. The chemical composition of the lava provided additional insights. Samples collected from floating pumice revealed that the magma was relatively primitive, meaning it had not spent much time in shallow chambers where it could mix with other rock types or lose its volatile gases. It was rising quickly and efficiently from depth. This explained the sustained nature of the eruption. The system was open and unobstructed. Magma could flow freely to the surface. But Nishinoshima was more than a scientific curiosity. It was a natural laboratory for studying how life colonizes barren landscapes. When the island first emerged, it was completely sterile. No plants, no animals, no microbes, just rock and ash. But nature does not wait long. Within months, scientists observed the first signs of life. Seabirds began landing on the island, resting during migrations. Their droppings introduced organic matter and nutrients. Seeds arrived, carried by wind and ocean currents. Some took root in cracks where ash had accumulated. By 2015, small patches of vegetation appeared on the older, more stable parts of the island. Hardy grasses and pioneer plants, species adapted to colonizing volcanic landscapes, began to establish themselves. Insects arrived, blown in on the wind or carried by birds. The island was becoming an ecosystem. It was a process that had occurred countless times throughout Earth's history, but rarely with such thorough documentation. Scientists could watch, step by step, as a lifeless rock transformed into a living landscape. The eruption also had broader implications. Nishinoshima was adding new land to Japan's territory. The island sits within Japan's exclusive economic zone, and its growth expanded the nation's maritime boundaries. This was not trivial. The waters around Nishinoshima contain valuable fishing grounds and potential mineral resources. The Japanese government formally incorporated the expanded island into its maps, recognizing it as sovereign territory. A volcano had literally redrawn the borders of a nation. But the eruption's most significant impact was on our understanding of volcanic island formation. Nishinoshima was not unique in geological history. Thousands of volcanic islands have formed this way over millions of years. The Hawaiian Islands, the Galapagos, Iceland, all began as submarine eruptions that eventually broke the surface. But in the modern era, such events are rare. The last comparable eruption was Surtsey, an island that emerged off Iceland in 1963. That eruption lasted 4 years and became one of the most studied volcanic events of the 20th century. Nishinoshima was following a similar trajectory, but with far more advanced monitoring technology. Scientists could now observe the island's growth in real time using satellites, drones, and remote sensors. They could measure gas emissions using spectrometers. They could track seismic activity with precision instruments. They could create three-dimensional models of the island's structure using photogrammetry and LiDAR. The data being collected was unprecedented in volume and detail. It would inform volcanic research for decades. By late 2015, the eruption began to show signs of slowing. Lava output decreased. The frequency of explosive events declined. Seismic activity beneath the island diminished. The island's growth, which had been relentless for 18 months, began to plateau. Scientists cautiously suggested the eruption might be entering a quieter phase. But they were careful not to declare it over. Volcanoes are unpredictable. A pause can last weeks, months, or years before activity resumes. Nishinoshima might rest. Or it might explode back to life without warning. In November 2015, the eruption officially paused. The lava stopped flowing. The ash plumes ceased. The island fell silent. For the first time since its birth, Nishinoshima was still. Steam continued to rise from vents and cooling lava flows, but the violent creation had stopped. The island had reached a temporary equilibrium. It now covered 2.7 square kilometers and rose 143 meters above the sea. It was a permanent addition to the Pacific, a new piece of the planet forged in fire. But the story was far from over. Nishinoshima had changed. The Pacific had changed. And thousands of kilometers away, Alaska's volcanoes were still rumbling. Pavlof volcano does not ask for attention. It demands it. Rising 2,700 meters above the Bering Sea, its near-perfect cone dominates the southwestern tip of the Alaska Peninsula. It is one of the most active volcanoes in North America, erupting on average every few years. But in March 2016, Pavlof entered a phase of activity that would remind the world why Alaska's volcanoes are among the most dangerous on Earth. The eruption began on March 27th. Seismic tremor had been building for days. A low-frequency vibration indicating magma movement deep beneath the mountain. Then, without warning, the summit exploded. Lava fountains burst from the crater, shooting incandescent rock hundreds of meters into the air. Ash plumes rose 9 kilometers above sea level, spreading eastward over the Gulf of Alaska. The Alaska Volcano Observatory immediately raised the aviation color code to red. Airlines scrambled to reroute flights. Pavlov's location makes it uniquely hazardous to aviation. It sits directly beneath flight paths connecting North America and Asia. Hundreds of flights pass near it every week, carrying tens of thousands of passengers. Volcanic ash is catastrophic for aircraft. It can melt in jet engines, solidifying on turbine blades and causing engine failure. In 1989, a KLM flight encountered ash from Alaska's Redoubt volcano and lost power in all 4 engines. The aircraft dropped more than 4 kilometers before the crew managed to restart the engines and land safely. Everyone survived, but the incident cost millions in repairs and lost revenue. Since then, aviation authorities treat volcanic ash clouds with extreme caution. Pavlov's 2016 eruption produced ash continuously for weeks. The plumes were dense and persistent, drifting hundreds of kilometers downwind. Satellite imagery tracked the ash clouds as they spread across the North Pacific. Airlines canceled flights. Cargo shipments were delayed. The economic impact mounted quickly. But for the people living near Pavlov, the concern was not flights or economics, it was survival. The nearest communities are Cold Bay and Nelson Lagoon, small villages with populations under 100. They sit on the eastern side of the Alaska Peninsula, separated from Pavlov by rugged mountains and impassable terrain. There are no roads connecting them to the rest of Alaska. Access is by air or sea only. If an eruption intensifies, evacuation options are limited. Residents must rely on small aircraft or boats, both vulnerable to weather and volcanic hazards. The indigenous Aleut people have lived in this region for thousands of years. They call Pavlov Pola, a name that predates Russian and American colonization. Their ancestors witnessed countless eruptions. They developed survival strategies passed down through generations. When the mountain erupts, you watch the wind. If ash is blowing toward you, you shelter indoors. You cover water supplies. You prepare to move if necessary. These are not written instructions. They are cultural knowledge embedded in stories and practices. During the March 2016 eruption, residents of Cold Bay monitored the activity closely. The village sits approximately 60 kilometers from Pavlov, far enough to avoid lava flows, but close enough to receive significant ashfall if the wind shifts. Ash is more than an inconvenience, it contaminates water. It damages machinery, it irritates lungs and eyes. Fine volcanic ash can cause respiratory problems, especially in children and the elderly. During heavy ashfall, visibility drops to near zero. Travel becomes impossible. Communities can be isolated for days. The Alaska Volcano Observatory maintained constant surveillance. Scientists analyzed seismic data in real time, looking for patterns that might indicate a shift in eruption style. They measured sulfur dioxide emissions using satellite sensors, tracking changes in gas output that could signal rising magma. They examined thermal images, identifying new lava flows and hotspots on the volcano's flanks. Every piece of data was evaluated, interpreted, and communicated to emergency managers and the public. But predicting volcanic behavior is not an exact science. Magma does not follow schedules. Eruptions can intensify suddenly or stop without warning. Pavlov had paused before, only to roar back to life days later. The scientists could describe what was happening. They could explain the mechanisms, but they could not predict precisely what would happen next. Uncertainty is inherent in volcanology. The best they could offer were probabilities and scenarios. On April 2nd, the eruption intensified. Explosions became more frequent and violent. Ash plumes reached 10 kilometers altitude. Lava flows extended further down the northern flank, glowing rivers visible from Cold Bay on clear nights. The aviation color code remained red. Flights continued to be rerouted. The eruption was now among the most significant Pavlov had produced in decades. Then, as suddenly as it began, the eruption weakened. By mid-April, lava output decreased. Ash emissions declined. Seismic activity dropped. The volcano was entering a quieter phase. The Alaska Volcano Observatory downgraded the aviation color code to orange, then yellow. Flights resumed normal routes. Communities began cleanup operations, sweeping ash from roofs and roads. But everyone knew this was not over. Pavlov had paused, not stopped. The 2016 eruption lasted approximately 3 weeks of intense activity, followed by sporadic, smaller eruptions over the following months. It was a reminder of the persistent threat volcanoes pose to Alaska. The state's economy depends on aviation. Its communities depend on supply chains vulnerable to disruption. And its volcanoes do not care about human schedules or needs. For scientists, Pavlov's 2016 eruption provided valuable data. High-resolution satellite imagery captured details of lava flow emplacement. Seismic networks recorded thousands of earthquakes, revealing the structure of the magma plumbing system. Gas measurements tracked changes in magma composition as the eruption evolved. All of this information improved understanding of how Pavlov behaves and how similar volcanoes might be predicted in the future. But the eruption also highlighted gaps in monitoring. Alaska has 52 active volcanoes. The Alaska Volcano Observatory has limited resources. Not every volcano has a full suite of instruments. Some rely on satellite monitoring alone, which can miss early warning signs. Funding is perpetually constrained. Scientists must prioritize which volcanoes receive the most attention, a decision based on risk but always involving difficult trade-offs. Pavlov, because of its activity level and proximity to air routes, is heavily monitored. But dozens of other Alaskan volcanoes could erupt with less warning. And when they do, the consequences could be far worse. Because in Alaska, the question is never if another volcano will erupt. It is when, and whether the world will be ready. Bogoslof rises from the sea on December 20, 2016. A new volcanic crisis began in one of the most remote corners of Alaska. Bogoslof Island, a tiny speck of rock in the Bering Sea, exploded back to life after nearly a century of dormancy. The eruption was sudden, violent, and unprecedented in the modern monitoring era. It would become one of the most intensely studied volcanic events in Alaskan history. Bogoslof sits in the Aleutian Arc, approximately 100 kilometers northwest of the fishing community of Unalaska. The island is small, less than half a square kilometer, and uninhabited except for nesting seabirds. It is the emergent summit of a massive submarine volcano rising 3,000 meters from the seafloor. Most of Bogoslof is underwater. What breaks the surface is merely the tip of a volcanic giant. The island has a violent history. It has erupted repeatedly over the past 2 centuries, sometimes destroying itself entirely before rebuilding. In 1796, the island was a single dome. By 1823, eruptions had split it into 2. In 1883, a major eruption created a new vent. In 1927, another eruption added more land. Each time the island changed shape, appearing and disappearing like a geological phantom. But after 1992, Bogoslof fell silent. For 24 years it showed no signs of activity. Scientists assumed it was dormant, perhaps for decades or longer. They were wrong. The first explosion on December 20th was detected not by seismometers but by lightning. Volcanic lightning is a phenomenon that occurs when ash particles collide in an eruption plume, generating static electricity. Lightning detection networks recorded intense electrical activity over Bogoslof. Scientists checked satellite imagery. The island was erupting. A massive ash plume rose 11 kilometers into the sky, spreading rapidly across one of the busiest air cargo routes in the world. The Alaska Volcano Observatory went into crisis mode. Bogoslof had no ground-based monitoring equipment. The island was too remote, too unstable, and too dangerous for permanent installations. Scientists had to rely entirely on satellite data, lightning detection, and infrasound sensors located hundreds of kilometers away. Infrasound detects low-frequency sound waves produced by explosions. The sensors could register eruptions at Bogoslof, but they provided limited detail. The observatory was essentially flying blind. Within hours, aviation authorities issued urgent warnings. The airspace around Bogoslof was closed. Flights were rerouted. Cargo planes carrying goods between North America and Asia were forced to take longer, more fuel-intensive routes. The economic cost was immediate and substantial. But there was no choice. Ash clouds from Bogoslof were dense and widespread. Any aircraft entering them risked catastrophic engine damage. The eruption did not stop. Over the following weeks, Bogoslof exploded repeatedly. Each eruption sent ash plumes soaring into the stratosphere. Some reached 15 kilometers altitude, high enough to spread across thousands of kilometers. Satellite imagery showed the plumes drifting eastward, occasionally reaching as far as the Alaskan mainland. The eruptions were phreatomagmatic, meaning seawater was interacting with rising magma. When seawater enters a volcanic vent, it flashes to steam instantly, amplifying the explosive force. The result is violent, unpredictable eruptions capable of producing enormous ash volumes. Scientists scrambled to understand what was happening. They analyzed satellite images frame by frame. They reviewed infrasound data. They compared the eruption to historical events. Slowly, a picture emerged. Magma was rising rapidly from depth, encountering the shallow ocean surrounding the island. The explosions were blasting through the seafloor, ejecting massive amounts of rock and ash. Each eruption was reshaping the island, adding new land or destroying old sections. Bogoslof was being rebuilt in real time. By early 2017, the eruption had become one of the most explosive volcanic events in Alaska in decades. Between December 2016 and August 2017, Bogoslof erupted more than 70 times. Each eruption was detected by lightning networks and satellites. Some lasted minutes. Others continued for hours. The ash plumes were so dense they appeared on weather radar, looking like thunderstorms but far more dangerous. For the Alaska Volcano Observatory, monitoring Bogoslof was a technological challenge. Without ground-based instruments, scientists had to develop new techniques. They used lightning data to estimate eruption intensity. They analyzed satellite thermal anomalies to track lava extrusion. They employed radar satellites to create three-dimensional models of the changing island. It was improvisation born of necessity, but it worked. The observatory issued timely warnings for nearly every major eruption. The eruptions also provided a rare opportunity to study phreatomagmatic volcanism in detail. This eruption style is common in submarine and shallow water volcanoes, but difficult to observe safely. Bogoslof offered a natural laboratory. Scientists documented how seawater access influenced eruption dynamics. They measured ash particle sizes and compositions. They tracked how the eruption plumes dispersed in the atmosphere. The data collected would inform volcanic hazard models for years. But the eruption was not just a scientific opportunity. It was a reminder of Alaska's vulnerability. Bogoslof is not near any communities, but its location beneath major air routes made it a critical threat. Every eruption forced flight cancellations and delays. Airlines lost revenue. Cargo deliveries were postponed. The disruptions rippled through global supply chains. A tiny island in the middle of the Bering Sea was affecting international commerce. By summer 2017, the eruptions began to wane. Explosions became less frequent. Ash plumes decreased in height. Seismic activity beneath the island declined. The Alaska Volcano Observatory cautiously lowered alert levels. Bogoslof was entering a quieter phase, though whether it was a pause or an end remained uncertain. The island had changed dramatically. New vents had opened. Old sections had collapsed. The coastline was unrecognizable compared to 2016. Bogoslof had once again rewritten its own geography. The eruption officially ended in August 2017, though scientists continued monitoring closely for signs of renewed activity. In total, the eruption lasted 8 months, producing over 70 explosive events and countless smaller emissions. It was the most active period in Bogoslof's recorded history. And it happened with almost no ground-based monitoring, a testament to both the challenges of Alaskan volcanology and the ingenuity of scientists working with limited tools. Bogoslof's eruption underscored a harsh reality. Alaska's volcanoes are among the least monitored in the developed world. Yet they threaten some of the most critical infrastructure. The state's aviation industry is essential for transporting goods, connecting communities and supporting the economy. Volcanic eruptions can shut it down with little warning. Improved monitoring could provide earlier alerts, but resources are limited. Scientists must make difficult choices about where to deploy instruments and personnel. And in Alaska, there are always more volcanoes waiting. The silent threat beneath, while Pavlof and Bogoslof captured headlines with their spectacular eruptions, another volcano in Alaska was showing signs of unrest that deeply concerned scientists. This volcano was not remote, it was not uninhabited. It sat directly adjacent to one of the state's most important communities. And its potential for catastrophic eruption was far greater than anything Pavlof or Bogoslof could produce. Akutan volcano rises from Akutan Island in the eastern Aleutians, less than 15 kilometers from the city of Unalaska. Unalaska, also known as Dutch Harbor, is home to approximately 4,500 people and one of the busiest fishing ports in the United States. The port processes billions of dollars in seafood annually. It is a critical hub for the Bering Sea fishing industry, supporting thousands of jobs across Alaska and the Pacific Northwest. And it sits in the shadow of an active stratovolcano that last erupted in 1992. Akutan is a textbook stratovolcano, steep-sided and symmetrical, built from layers of lava and ash deposited over thousands of years. Its summit rises 1,300 meters above sea level, crowned by a small caldera formed during a collapse thousands of years ago. The volcano is part of the Aleutian Arc, the same subduction system feeding Pavlof, Bogoslof, and dozens of other Alaskan volcanoes. But Akutan is different. It sits closer to a major population center. And its eruption history suggests it is capable of far more than the relatively gentle lava flows seen at Pavlof. In early 2017, seismic activity beneath Akutan increased. Small earthquakes clustered beneath the summit, occurring in swarms that lasted hours or days before subsiding. This pattern repeated throughout the year. The earthquakes were shallow, typically less than 5 kilometers deep, indicating movement of magma or hydrothermal fluids near the surface. The Alaska Volcano Observatory monitored the activity closely, issuing regular updates to local authorities and the public. Then, in 2018, the unrest intensified. Earthquake swarms became more frequent and energetic. Seismometers recorded tremor episodes, the continuous vibration associated with fluid movement underground. Satellite measurements detected slight deformation of the volcano's flanks, suggesting magma was accumulating beneath the surface. These were classic signs of volcanic unrest. They did not guarantee an eruption was imminent, but they indicated the volcano was restless. For the residents of Unalaska, this was not abstract. An eruption at Akutan could devastate the community. Ashfall could blanket the city, contaminating water supplies and shutting down the airport. Pyroclastic flows could sweep down the volcano's flanks, reaching the coast in minutes. Lahars, volcanic mudflows triggered by melting snow or heavy rain mixing with ash, could inundate valleys and destroy infrastructure. And if the eruption were large enough, it could generate a tsunami by triggering a flank collapse or underwater explosion. The Alaska Volcano Observatory worked with local emergency managers to develop contingency plans. Evacuation routes were mapped. Shelter locations were identified. Communication protocols were established. But planning for a volcanic disaster in Alaska is complicated. Unalaska is isolated. The only access is by air or sea. In winter, storms can shut down both for days. Evacuating thousands of people on short notice would be logistically challenging and potentially impossible if weather did not cooperate. The city also had economic concerns. Unalaska's economy depends on fishing. The ga operates year-round, processing crab, pollock, and other seafood. A major eruption could shut down operations for weeks or months. The financial impact would be catastrophic, not just for Unalaska but for the entire Bering Sea fishing industry. Insurance companies began reassessing risk. Businesses developed contingency plans. Everyone was preparing for a disaster that might never come. But the volcano continued its slow escalation. By mid-2018, gas emissions from the summit increased. Sulfur dioxide, a key indicator of magma degassing, was detected in elevated concentrations. Thermal cameras mounted on the volcano's flanks recorded increased heat flow from fumaroles near the summit. The mountain was warming. Something was happening deep below. Scientists debated what the signals meant. Some believed an eruption was likely within months. Others argued the unrest could continue for years without producing an eruption. The data was ambiguous. Volcanic unrest is common. Many episodes resolve without eruption. Magma can intrude into shallow crust, causing earthquakes and deformation, then cool and solidify without reaching the surface. Predicting which unrest episodes will lead to eruptions is one of the greatest challenges in volcanology. The Alaska Volcano Observatory increased monitoring efforts. Additional seismometers were deployed around the volcano. A permanent GPS station was installed to measure ground deformation with millimeter precision. Gas monitoring equipment was upgraded. A webcam was positioned to provide real-time visual surveillance. The observatory was doing everything possible with limited resources. But Akutan remained fundamentally under-monitored compared to volcanoes in places like Japan or Italy, where dense instrument networks provide far more data. Throughout 2019, the unrest continued. Earthquake swarms occurred every few weeks. Deformation persisted, with the volcano's flanks slowly inflating as magma accumulated below. But no eruption occurred. The volcano was building towards something, but what and when remained uncertain. Residents grew accustomed to the frequent earthquake alerts. Life continued. Fishing boats came and went. The port operated normally. But everyone knew the situation could change in hours. Then, in early 2020, something unexpected happened. The seismic activity decreased. Earthquake frequency dropped. Deformation slowed. Gas emissions declined. The volcano was quieting. Scientists cautiously suggested the unrest episode might be ending. Perhaps the magma intrusion had stalled. Perhaps the system was stabilizing. Or perhaps this was just a pause before a larger event. By late 2020, Akutan had returned to background levels of activity. The volcano was still being monitored, but the immediate threat seemed to have passed. No eruption occurred. The community had prepared for a disaster that never came. Some saw this as wasted effort. Others recognized it as a successful example of hazard preparedness. The volcano had not erupted, but the response had been appropriate given the signals. Yet the episode left unresolved questions. Why did the unrest begin? Why did it stop? How much magma had intruded, and where was it now? Was it cooling harmlessly underground or accumulating for a future eruption? These questions had no definitive answers. The data was insufficient. The processes occurring kilometers beneath the surface remained largely invisible. Akutan's unrest highlighted a fundamental truth about volcanic hazards. Uncertainty is unavoidable. Scientists can monitor volcanoes. They can detect unrest. They can issue warnings. But they cannot predict eruptions with precision. Every volcano is different. Every eruption is unique. The best scientists can offer are probabilities and scenarios, not certainties. And in Alaska, where dozens of active volcanoes threaten communities, infrastructure, and aviation, that uncertainty is a permanent condition. The volcanoes will erupt again. Some will give warning. Others will not. The only certainty is that the Earth is not finished. And neither is the story. Nishinoshima reawakens while Alaska's volcanoes commanded attention in the northern Pacific. Nishinoshima had not been forgotten. The island had rested quietly since late 2015, steaming gently but showing no signs of renewed eruption. Scientists continued monitoring it via satellite, documenting the gradual colonization by plants and seabirds. The island seemed stable, a completed chapter in the story of the Pacific Ring of Fire. But volcanoes do not follow scripts. And in December 2017, Nishinoshima came roaring back to life. The reawakening began with increased thermal activity detected by satellite sensors. Heat signatures at the summit intensified, indicating fresh magma reaching shallow levels. Within days, explosions resumed. Lava fountains burst from the central crater, arcing into the sky exactly as they had in 2013. Ash plumes rose thousands of meters, drifting on Pacific winds. The island was erupting again, and this time it would not stop for years. The renewed eruption was more vigorous than the first. Lava output increased dramatically. Multiple vents opened around the summit, each feeding flows that raced down the slopes toward the ocean. The island expanded rapidly, adding hundreds of meters of new coastline within months. By mid-2018, Nishinoshima had grown to nearly 3 square kilometers, larger than before. The mountain was building itself higher and wider, consuming its own earlier landscape in rivers of molten rock. Japanese scientists returned to the exclusion zone aboard Coast Guard vessels. They could not land, the island was too dangerous, but they could observe from close range. What they saw astonished them. The eruption was sustaining itself with remarkable consistency. Lava was being produced at rates comparable to major Hawaiian eruptions. This was not a brief pulse of magma. It was a long-term outpouring, suggesting the deep plumbing system feeding the volcano had stabilized into an efficient conduit from mantle to surface. The ecological story that had begun during the first eruption was now obliterated. The vegetation that had taken root was buried under fresh lava. The seabirds that had colonized the island fled. Nishinoshima was reset to zero, a sterile landscape of glowing rock and toxic gas. But this was not a setback in geological terms. It was a continuation. The island was still being built. The ecosystems would return when the eruption ended. Life is patient. It had waited millions of years before. It could wait a few more. The chemical composition of the new lava was similar to the earlier eruption, confirming that the same magma source was active, but there were subtle differences. The lava contained slightly more evolved minerals, suggesting some mixing or differentiation had occurred in the magma chamber. This indicated the subsurface system was complex, with magma residing at multiple depths and undergoing chemical changes before reaching the surface. Understanding these details helped scientists reconstruct the volcano's internal architecture. By 2019, Nishinoshima had become one of the most closely watched volcanoes on Earth. Not because it threatened human populations, it remained uninhabited and remote, but because it offered unparalleled insights into volcanic island formation. Modern technology allowed continuous monitoring at a level impossible during previous island-building eruptions like Surtsey. Satellites provided daily images. Thermal sensors tracked heat output. Gas spectrometers measured sulfur dioxide emissions. The data stream was constant and rich. Researchers from universities across Japan collaborated on Nishinoshima studies. They published papers on lava flow dynamics, eruption forecasting, and ecosystem recovery. International scientists joined the effort, contributing expertise in satellite remote sensing and volcanic gas analysis. Nishinoshima became a global research project, a natural laboratory accessible to anyone with the right instruments and questions. The eruption also reignited discussions about territorial implications. As the island grew, so did Japan's exclusive economic zone. The expanded landmass provided legal justification for extending maritime boundaries, granting Japan rights to fish, minerals, and other resources in surrounding waters. This was not merely academic. The Western Pacific contains valuable fisheries and potential mineral deposits. Volcanic islands, even small ones, carry geopolitical weight. But the eruption was not without challenges for monitoring. The island's remoteness limited access. Weather in the region is notoriously poor, with frequent storms and high seas. Satellite observations were occasionally obscured by clouds. The exclusion zone prevented close-range study. Scientists had to work with whatever data they could acquire from distance, accepting gaps and uncertainties. Yet, despite these limitations, the monitoring program was remarkably successful. One of the most significant findings was the eruption's longevity. By 2020, Nishinoshima had been erupting intermittently for 7 years, with only a brief pause in 2015 and 2016. This placed it among the longest sustained eruptions of the 21st century. Few volcanoes maintained such consistent output for so long. The fact that Nishinoshima could do so indicated its magma supply was both large and reliable. Deep beneath the Pacific seafloor, A massive reservoir was feeding the surface eruption with no sign of exhaustion. In August 2020, the eruption intensified yet again. Explosions became more violent. Ash plumes reached higher altitudes. Lava flows accelerated, pouring into the ocean at multiple locations simultaneously. The island's growth rate increased. By the end of 2020, Nishinoshima covered nearly 4 square kilometers and rose over 200 meters above sea level. It was no longer a small volcanic island. It was a substantial mountain, visible from dozens of kilometers away, its summit often shrouded in ash and steam. The eruption's environmental impact extended beyond the island itself. Volcanic aerosols and gases entered the atmosphere, contributing to regional air quality changes. Ash fell on distant islands, though in small amounts. The ocean surrounding Nishinoshima was enriched with volcanic nutrients, particularly iron, which can stimulate phytoplankton growth. This effect, known as volcanic fertilization, has been observed at other marine eruptions. It temporarily boosts primary productivity in nutrient-poor ocean regions, cascading through the food web. By mid-2021, the eruption began showing signs of decline, lava output decreased. Explosions became less frequent. Seismic activity beneath the island diminished. Scientists speculated the eruption might be entering another pause, similar to 2015. They were cautious, knowing the volcano had surprised them before. But the data suggested the current eruptive phase was winding down. The magma supply, while not exhausted, seemed to be throttling back. In October 2021, the eruption stopped. Lava flows ceased, ash emissions ended. Nishinoshima fell silent once more. The island was larger, taller, and more robust than ever before. It had survived 2 major eruptive phases and emerged as a permanent fixture of the Pacific landscape. Whether it would erupt again remained an open question. But for now, it rested. The story of Nishinoshima is not finished. The volcano remains active in geological terms. It sits atop a subduction zone that will continue feeding magma for millions of years. Future eruptions are inevitable. But the island has already achieved something remarkable. It has shown the world, in real time and extraordinary detail, how the Earth builds itself, how continents begin, how mountains rise, how life finds a way. And it has reminded us that the Pacific Ocean, vast and seemingly unchanging, is anything but still. The eruptions of Nishinoshima, Pavlof, Bogoslof, and dozens of other volcanoes across the Pacific Ring of Fire between 2013 and 2021 were not isolated incidents. They were expressions of a single, interconnected system. The Earth's crust is not a collection of separate pieces operating independently. It is a dynamic skin stretched over a molten interior, constantly shifting, breaking, and rebuilding. And the volcanoes are where that hidden violence becomes visible. The Pacific Plate, the largest tectonic plate on Earth, drives this system. It spreads from the East Pacific Rise, a massive underwater ridge where new oceanic crust is born, and travels westward at rates of up to 10 centimeters per year. Along its margins, it collides with other plates, diving beneath them in subduction zones that circle the Pacific like a noose. As the plate descends, it melts, feeding magma chambers that supply hundreds of active volcanoes. This process has been ongoing for hundreds of millions of years. It will continue for hundreds of millions more. What makes the modern era unique is our ability to observe this process in unprecedented detail. A century ago, volcanic eruptions were local disasters, documented by survivors and occasional scientists who happened to be nearby. Communication was slow, data was sparse, understanding was limited. Today, satellites monitor every volcano on Earth continuously. Seismic networks detect earthquakes in real time. Gas sensors measure emissions remotely. Global communication networks share information instantly. We can watch the planet's volcanic activity as it unfolds, integrating data from thousands of sources to build a comprehensive picture. This capability has transformed volcanology from a descriptive science to a predictive one. Scientists can now forecast some eruptions days or weeks in advance, providing warnings that save lives and reduce economic losses. The Alaska volcano. Observatories' monitoring of Pavlof and Bogoslof allowed timely alerts that prevented aviation disasters. Japan's surveillance of Nishinoshima enabled detailed study of island formation. These achievements represent decades of investment in monitoring infrastructure and scientific research. They are success stories, but they also reveal how much remains unknown. Despite advanced technology, volcanologists still cannot predict most eruptions with precision. The unrest at Akutan in 2017 and 2018 could have led to a catastrophic eruption. It did not. No current model can definitively explain why. Bogoslof erupted more than 70 times in 8 months, each explosion detected only minutes before it occurred. Improved monitoring might provide hours of warning instead of minutes, but the fundamental unpredictability remains. Magma does not follow deterministic rules. Volcanic systems are chaotic, sensitive to tiny perturbations that cascade into large effects. This uncertainty is not a failure of science. It is a recognition of complexity. The Earth's interior is largely inaccessible. We can drill a few kilometers into the crust, but magma chambers exist tens of kilometers deep. We infer their properties from indirect measurements, seismic waves, gravity anomalies, gas emissions, but we cannot observe them directly. We build models based on physics and chemistry, but those models are simplifications of processes occurring at extreme temperatures and pressures. Every eruption provides new data that refines understanding, but also reveals new complexities. The eruptions between 2013 and 2021 contributed enormously to this growing body of knowledge. Nishinoshima demonstrated how rapidly volcanic islands can form and evolve. Pavlof showed how sustained lava fountaining can persist for weeks. Bogoslof revealed the explosive power of phreatomagmatic eruptions in shallow water. Akutan illustrated how volcanic unrest can escalate and then subside without eruption. Each event was a natural experiment, providing insights impossible to replicate in laboratories. But the most important lesson from these eruptions is not scientific. It is humbling. The Earth operates on timescales and energy levels that dwarf human experience. A volcano like Nishinoshima can build an island in months, work that would take human engineers decades and billions of dollars. Pavlov can erupt for weeks, releasing energy equivalent to thousands of nuclear weapons. Bogoslof can explode dozens of times, each event powerful enough to disrupt global aviation. These are not anomalies. They are routine expressions of planetary processes. And they will continue. The Pacific Ring of Fire is not calming. Subduction continues. Magma rises. Volcanoes grow. Some are monitored closely. Others are barely watched. Many will erupt in the coming years. Some eruptions will be small and inconsequential. Others will be catastrophic. The only certainty is that they will happen. The Earth does not rest. For the people living in the shadow of these volcanoes, this reality is inescapable. In Alaska, communities exist on the flanks of active mountains because the land is beautiful, the resources are abundant, and the alternatives are elsewhere. In Japan, millions live on volcanic islands because that is where their ancestors settled centuries ago. These are not reckless choices. They are calculated risks, balanced against the benefits of living in these places. Volcanic soils are fertile. Geothermal energy is abundant. The landscapes are stunning. And for most of human history, volcanic eruptions have been rare events, separated by generations. But as populations grow and infrastructure becomes more interconnected, the consequences of eruptions escalate. A volcano in Alaska can shut down aviation across the Pacific. An eruption in Japan can disrupt global supply chains. The world is more vulnerable to volcanic hazards than ever before, not because volcanoes are more dangerous, but because human systems are more fragile. A single ash cloud can ground thousands of flights. A single tsunami can devastate coastlines. A single lahar can destroy a city. The hazards have not changed. The exposure has. This is why monitoring matters. Why research matters. Why investment in volcano observatories and hazard mitigation is essential. We cannot prevent eruptions. We cannot control volcanoes. But we can prepare, we can monitor, we can warn. We can reduce risk even if we cannot eliminate it. The Alaska Volcano Observatory operates on a fraction of the budget needed for comprehensive monitoring. Yet it provides critical services that protect lives and economies. Expanding that capability in Alaska and globally is not optional. It is necessary. The eruptions of Nishinoshima and Alaska's volcanoes remind us of something easily forgotten in the modern world. We live on a dynamic planet. The ground beneath our feet is not solid and unchanging. It is a thin crust floating on molten rock, constantly deforming and occasionally breaking. Volcanoes are the visible proof of this violence. They are not disasters waiting to happen. They are the planet's natural state. They are how the Earth releases heat, builds continents, and recycles its crust. They are essential to the processes that make this planet habitable, and they are beautiful. The glowing rivers of lava pouring down Nishinoshima's flanks, the towering ash plumes rising from Pavlof, the explosive birth of new land at Bogoslof. These are not just hazards. They are spectacles, moments when the planet's hidden power becomes visible. They inspire awe and fear in equal measure. They remind us that we are small, temporary, and utterly dependent on forces we do not control. The story of Nishinoshima and Alaska's volcanoes is not finished. It will never be finished. As long as the Earth's interior remains hot, as long as tectonic plates continue moving, volcanoes will erupt. New islands will rise. Old mountains will collapse. The cycle will continue, indifferent to human presence. We are witnesses to this process, observers in a drama that began billions of years ago and will continue long after our species is gone. But for now, we watch, we measure, we learn, we prepare, and we marvel at the violent beauty of a planet that is very much alive. If you want to continue exploring the restless power of our planet, subscribe to Fury of the Earth and join us on the next journey into the heart of the fire.